All right, welcome everybody, and finally I've got some time to make this video for you. I'm going to kind of quickly go through the questions on the review and give you some of the details, some of the stuff I'm going to say, set up the integral, and some of these I'm just going to say are fairly easy to evaluate once you get them set up. So for the very first one, this one is you've got a vector field defined as negative 1i plus xj. Find the line integral along a line segment. So what I would hope you would do is start out by parameterizing that line segment and say r of t, where x and y are going to be parameterized in terms of t. Right, and remember that when we do a line segment, we start from one point. The beginning point is going to be the constant terms in the equations. And then the displacement, when we go from 1, 0 to 0, 1, the x is going to decrease by 1. So this is going to be minus 1t. And then the y is going to increase from 0 to 1. So it's going to be plus t. And then with a line segment, you can always set this up so that t goes from 0 to 1 that way. All right, and then the other thing we're going to need is r prime of t. And r prime of t is just simply the derivatives of these. So the derivative of x is going to be minus 1. The derivative of y is going to be positive 1. Okay, so then once you get those established, then to evaluate the line integral, we're going to say t goes from 0 to 1. And then we're going to take the vector field, okay, the negative 1 and the x, and we're going to substitute in the parameterization. So the negative 1 is going to be negative 1, but the x is going to be 1 minus t. And then we're going to dot that with the derivatives, so negative 1 and 1, and then with respect to t. All right, so when you take the dot product, you're going to get the integral from 0 to 1. Negative 1 times 1 is going to give me 1, plus 1 times 1 minus t is going to give me 1 minus t. All right, and then we're going to integrate this with respect to t. All right, so this is going to be from 0 to 1, and this is basically 2 minus t then, dt. An antiderivative of 2 is going to give me 2t minus 1 half t squared from 0 to 1. It's going to give me 2 minus a half is 3 halves. Okay, so 3 halves is the line integral along that path. Okay, then part B is very similar. The only difference is that we're going to be traversing along a circle in a counterclockwise direction from the point 2, 0 to the point negative 2, 0. And it says along a counterclockwise direction, so we're going to go up and over the top this way. So the parameterization of this path is going to be that r of t is x is along a circle of radius 2 would be 2 cosine t, and y will be 2 times the sine of t. And if we go halfway around the circle, that means that t is going to go from 0 to pi. All right, so then r prime of t is just the derivatives of those. So x prime and y prime. X prime is going to be negative 2 sine t. Y prime is 2 cosine t. All right, and then again, we're going to plug into the vector field and then integrate this from 0 to pi. All right, so the vector field again is negative 1 and x is 2 cosine. And then that's going to get dotted with the derivatives, so negative 2 sine and 2 cosine dt. All right, so when I take the dot product of this, I'm going to get negative 2 sine is going to get multiplied by negative 1. So we'll get 2 sine t. And then we're going to get plus 4 cosine squared t dt from 0 to pi. All right, now a couple of you asked me about this one and how do you integrate cosine squared? And you're going to really need a trig identity for this one. And so I'm going to say don't worry about this for the exam. If you need it, I'm going to give it to you. You don't have to have it memorized, but it comes from the double angle formula where cosine squared t is going to be equal to 1 half times the cosine of 2t and plus 1. All right, so 4 times this is going to be an integral from 0 to pi, and then 2 sine t. And if I take 4 times what I have over here, that's going to give me plus 2 cosine of 2t. And then this is going to give me plus a half times 4 is going to give me plus 2 dt. An antiderivative of this now is going to give me, an antiderivative of 2 sine is going to give me negative 2 cosine. And then an antiderivative of this is going to give me sine of 2t, and it'll be positive. And then plus an antiderivative of 2 is 2t, and then we're going to go from 0 to pi. Alright, so when you plug in, you're going to get negative 2 times the cosine of pi is going to give me negative 2 times negative 1. The sine of 2 pi is going to give me 0. And then this is going to give me plus 2 pi. And then I'm going to subtract what I get when I plug in 0. The cosine of 0 is 1, so this is going to give me minus 2 times 1. And then the sine of 0 and 2 times 0 are both going to give me 0. All right, so when I simplify this, this is going to give me 2, and this is going to give me plus 2 more, so that's going to give me 4, and then plus 2 pi. Okay, again, don't worry too much about this. If you need it, I'll give it to you, but that's the way that you're going to handle that one with the square on the cosine. Okay, then for part C, this is really no extra work. It's just that you're going to change this so that we're going all the way around the circle instead of just halfway. So the only thing you're going to change is this is going to be an integral from 0 to 2 pi instead. So when we get down to this point, we're going to do exactly the same steps down to here, but it's going to be 0 to 2 pi, and then 2 sine t plus 2 cosine 2t plus 2. An antiderivative of that is still negative 2 cosine t, and then plus sine of 2t plus 2t, and now we're going to go from 0 to 2 pi. Alright, so when you plug in, you're going to get negative 2 cosine of 2 pi is 1, plus the sine of 4 pi is 0, and then this is going to give me 2 times 2 pi is plus 4 pi. And then we're going to subtract what we get when we substitute 0 in, so that's going to give me negative 2 cosine of 0 is just going to give me negative 2. And then the sine of 0 and 2 times 0 are both going to give me zeros. Alright, so the negative 2 and the positive 2 over here are going to cancel out. We're going to be left with 4 pi. Okay, so just a tweak on part B, you're going to change that to 2 pi. Alright, so now this is over a closed path. It's a closed circle of radius 2. And so now this question says use Green's theorem to find the answer. So Green's theorem says to find the curl. So we're going to take the partial with respect to x of f2, which is x, minus the partial with respect to y of f1, which is negative 1. Okay, so the curl ends up giving me 1 minus 0. And then Green's theorem says to set up an integral over this, in this case, a circle. All right, so if I'm going to do that over a circle, I think I want to do this in polar coordinates. So we're going to say r goes from, this is a circle of radius 2, so r goes from 0 to 2, and theta is going to go from 0 to 2 pi. We're going to integrate 1, but now we've switched this into polar coordinates, so it's going to be r dr and then d theta. All right, so I'm going to continue and evaluate this one. This is going to give me the integral from 0 to 2 pi. An antiderivative of r is 1/2 r squared from 0 to 2 and then d theta. So half of 4 is 2 from 0 to 2 pi. D theta is going to give me 2 theta from 0 to 2 pi, and I get 4 pi for an answer. Okay, had we got a different answer than we got in part C, that should tell us, hey, we did something wrong on one of those, and we have to go back and find where the error is. Okay, so that's one of the examples of using Green's theorem then. Okay, moving on to the next page. This one is, I got a vector field in 2 space again, and it says to evaluate the line integral directly. All right, so this is kind of like the same question that we did last. We're going to parameterize the path. So r of t is the parameterization of this is in terms of x and y. So again, I'm going to start out with x is 1 and y is 0. X is going to decrease by 1, so give me negative t, and y is going to increase by 1, so plus t. And then this is going to be where t goes from 0 to 1. All right, and then we're going to also need the derivatives of those. So x prime of t and y prime of t are going to be negative 1 and 1. Okay, this is the same path that we took on the previous problem. Okay, this one says evaluate this directly. So we're going to end up with an integral from 0 to 1. I'm going to substitute in the parameterization here is 1 minus t for x and t for y. So 2xy is going to give me 2 times 1 minus t times t plus 3 is the I component. And then x squared is 1 minus t quantity squared. That's going to get dotted with the derivatives again, so negative 1 and 1, and then dt. All right, so when you simplify this, you're going to get an integral from 0 to 1. This mess here is going to simplify into, let's see, it's going to give me 2t squared. It's going to give me a plus 2t and minus 3. Okay, is what you get when you multiply all this out up here. And then also multiply by negative 1. All right, and then if you take 1 times this, you're going to get plus, if you FOIL this out, you're going to get 1 minus 2t plus t squared dt. All right, so that's what you should get when you do the dot product and you simplify everything. Okay, so this is going to give me an integral from 0 to 1. I'm going to combine all my terms. I'm going to end up with 2t squared, and a t squared is 3t squared. Okay, I'm also going to end up with the 2t, and the negative 2t is going to go away. And we're going to end up with a minus 2 dt. Yeah, minus 2 dt. All right, so when I evaluate this, I'm going to get an integral of 3t squared is t to the third minus, I think I've got something wrong here. Let's see. Let's see. 2t squared. All right, let me check this again. This is going to give me 2t squared. This is my mistake. This is minus 2t and minus 3. Okay, and then let's see if I combine these. I'm going to also end up with a term in here that is a negative 4t. Okay, so an antiderivative of this is t to the third. This is going to give me a negative 2t squared and then minus 2t. Yeah, I messed up this sign here. This is going to give me two negative 2t's, and it's going to give me negative 4t. Okay, so an antiderivative of this is that, and we're going to go from 0 to 1, and we'll have 1 minus 2 minus 2. And if I plug in 0, I get 0, and that's going to give me negative 3 for an answer. Okay, so that one ends up being a little bit tricky to get up to the answer. Then part B says, show that this is conservative. All right, now, I know that on the quiz, some of you showed that something was conservative by going back and finding the potential function. And there's nothing wrong with that, but if the question is just to show that it's path independent, all I really need to do is look at the curl. So it's going to be the derivative of f2 with respect to x minus the derivative of f1 with respect to y. All right, and I want to compare this to 0. So the derivative of f2 with respect to x is going to give me 2x. The derivative of f1 with respect to y is going to give me 2x, and that gives me 0. Okay, so since the curl, partial of f2 with respect to x minus the partial of f1 with respect to y is equal to 0, then the vector field is path independent. Okay? So if the vector field's path independent, that means that there must be a potential function, right? And what I know about that potential function is that fx must be the horizontal component of that, so 2xy plus 3, which tells me that the function must be an antiderivative of this, so x squared y plus 3x plus possibly a function of y. All right, then if I take the partial derivative with respect to y, I'm going to get x squared plus 0 plus g prime of y, and I'm going to compare that to the the j component up here, which is just x squared. All right, which tells me that g prime has to be equal to 0, which just tells me that g of y must be just a constant. Okay, so my potential function then is just going to be this x squared y plus 3x. Okay, and then this is just going to be a constant. Okay, so now to find this integral using the fundamental theorem of line integrals, all I have to do is take x squared y plus 3x, and we're going to plug in the terminal point, which is 0, 1, plug in the initial point, 1, 0, and evaluate. All right, so if I plug in x is equal to 0, if x is equal to 0, both these are going to end up being 0. And if I plug in 1, 0, this is going to be 0 and 3. And I get negative 3 for an answer. All right, and then again, we should expect to see this answer and this answer should be the same. Right? So once you find the potential function, this method is a lot easier to find that line integral than parameterizing the path. Okay, moving on. Next question is a three-dimensional vector field. It says evaluate this directly. All right, so to do this directly, you're going to find the parameterization of the path again. All right, this is a linear path between these 2 points, so we're going to find parametric equations for this line segment in 3 space. So I'm going to start with, again, like what I did, 1, 0, 0, and then think about the displacement vector. X is going from 1 to 2, so that's an increase of 1, t. Y is going to go from 0 to 2, that's an increase of 2 times t. And z is going from 0 to 1, that's an increase of 1t. All right, then t is going to be bound by 0 and 1. All right, so you're going to take the derivatives of those next, and x prime and y prime and z prime are going to be the derivatives of these functions, so namely 1 and 2 and 1. Okay, so now to find this line integral, you're going to end up setting up an integral from 0 to 1. We're going to take the vector field that's given to us and we're going to substitute in the parameterization. So this will be 2 times 1 plus t plus 3. And then y squared will be 2t quantity squared, so 4t squared. And then the third component is going to be y plus z, so 2t plus t is 3t. We're going to dot that with 1, 2, and 1, and then integrate with respect to t. All right, so when you take the dot product of this, you're going to get this times 1, this times 2, and this times 1, and you're going to end up with, let's see, 2 plus 2t plus 3, that's going to give me 5 plus 2t. And then if I double this, I'm going to get plus 8t squared, and then plus 3t dt. All right, and then take an antiderivative of this. An antiderivative of this is going to give me 8 thirds t cubed. And then I've got 2t and 3t is 5t. An antiderivative of that's going to be 5 halves t squared. And then I've also got a plus 5. And we're going to go from 0 to 1. All right, so I'm going to get 8 thirds plus 5 halves plus 5. All right, and then if I want to simplify that, I suppose I could say the common denominator is going to be 6. 8 thirds is the same as 16 6. 5 halves is the same as 15 6, and 5 is the same as 36. And so if you add these up, you're going to get, what, 31 and 30 is 61 over 6. Okay, so 61 6 would be the answer to that one. Okay, and then that one doesn't have any other parts to it, so let's go on to number 4. This one now, we're getting into, this is F dot dA. This is finding the flux over this surface. All right, so for this one, it says that find the flux over a surface which is a rectangle in the xz plane. So in the xz plane, we've got something like this. X is going to go from 0 to 1, and z is going to go from 0 to 2. All right, so we've got a region that looks like this, and then the y-axis goes out this way. And it says S is oriented in the direction of positive y. Okay, so to set this one up then, I'm going to set this one up as if it's an integral, a flux integral. This is going to be in terms of x and z. So let's say that x goes from 0 to 1, and z is going to go from 0 to 2. The vector field is up here as negative y I plus 1j plus zk. And everywhere in this xz plane, I know that y is going to be 0. So I'm going to substitute 0 in for the y, and then 1 and z. And then we're going to dot this with the area vector. All right, now for this one, the area vector is pretty easy. It's just going to be, the area vector is going to be this patch, and then dotted with a vector that points in the I direction. So, I'm sorry, in the y direction, which would be the j direction, would be 0, 1, 0. And then the dimensions of this patch are going to be just delta x and delta z. So dx and dz. All right, so when you take the dot product here, you're going to get the integral from 0 to 2, from 0 to 1. The dot product is going to be just 1 dx and dz. All right, and then again, we've mentioned this a couple times, that if you integrate a constant, all you have to do is take the area of this and multiply it by 1, and you're going to get that the area of this is 2 times 1 is going to give me just 2 for an answer. Okay? If you didn't realize that, you could go through and take an antiderivative of 1 and plug in and run it through, but this is a quick way to get to the answer. Okay, then for the next part in this one, we're finding again a flux integral where S is a rectangle in the plane x equals 2. All right, so if I draw that picture, x equals 2 is going to come out here. It says y goes from 0 to 1, and z is going to go from 0 to 2. All right, so that rectangle is going to look something like this, and is oriented in the direction of positive x, so it's coming out this way. Okay, so again, I'm going to set up an integral. This is going to be in the yz plane, so I'm going to say my limits on y are going from 0 to 1, and z are going from 0 to 2. All right, so now on this plane, I know that x is equal to 2, and if I go back to my vector field, then I'm going to replace all the x's with 2's, but there are no x's in here, so this is just going to be negative y and 1 and z. And that's going to get dotted with a vector that points towards me. In the x direction is going to be 1, 0, 0. And then the dimensions of that patch are going to be dy and dz. All right, so we're going to get an integral from 0 to 2, and from 0 to 1, we're going to end up only picking up negative y, dy, dz. And the antiderivative of that's going to be negative 1/2 y squared from 0 to 1, dz, 0 to 2. Plug in the 1, you're going to get negative 1/2 dz from 0 to 2. So you get negative 1/2 times z from 0 to 2, and that's going to give me negative 1 for an answer. Okay, so you could have done this one a little bit differently. Because you end up picking up 1 here, you could have just said take the whole vector, take that whole area, and say that this is going to be an area vector whose magnitude is 0, 2, 0, and then just dot it with the with this vector field, and you're going to come up with 2 for an answer also. All right, it seems like most of you would rather think of just a process here that's going to work for both of these, and I would say you're probably safe doing it that way. Okay, moving on. This one says, again, find, this is a flux integral. where S is the part of the plane, Z equals 2 plus X plus 3Y, and it's above a region in the XY plane oriented in the direction of positive Z. Okay, so for this one, we want to parameterize this surface. And so when I parameterize this surface, I'm going to say, let's do this in terms of this equation just tells me that Z is going to be equal to 2 plus X plus 3Y, which means X is X and Y is Y. All right, so the parameterization of this is going to be in terms of X and Y. And then our parameterized region is going to be that X goes from 0 to 1 and Y goes from 0 to 2. Okay, now if you imagine that there's a surface above here, if you move in the X direction, you're going to go this way. If you move in the Y direction, you're going to go this way. If you're looking down on this surface from above, you're going to take the cross product of Rx with Ry in that order. All right, so the derivatives with respect to X are going to be 1, 0, and 1. And the derivatives with respect to Y are going to be 0, 1, and 3. And then times then the cross product of these. So when you take that cross product, you're going to get 0 minus 1. You're going to get 3 minus 0 and then change the sign. And then you're going to get 1. And this is times dx and dy. Okay, if you're one of those people that like the formula that's in the book, this formula still works. It says find the derivative with respect to x and then change the sign. Find the derivative with respect to y and change the sign, and 1. All right, so if you wanted to, you could have got there without doing the cross product. Okay, so now we need to take an integral over this region. Y is going to go from 0 to 2, and x is going to go from 0 to 1. We take the vector field, which is defined up here, is negative y, 1, and z is going to get replaced with 2 plus x plus 3y. That's going to get dotted with negative 1, negative 3, and 1, dx, dy. All right, so when you take that dot product, you're going to get 0 to 2 and 0 to 1. This negative is going to get multiplied by negative y, so that gives me y. The 1 is going to get multiplied by negative 3. And then 1 is going to get multiplied by the rest of this, 2 plus x plus 3y dx dy. And I'm going to tell you that this is going to be easy for everybody to evaluate, and you shouldn't get 7 for an answer. Okay, so the work there is again, I think it's kind of trivial for most of you to do that at this point. Okay, then for part D, we've still got this same vector field. Now it says find the flux out of a cube that is 1 by 1 by 1. All right, so we've got a three-dimensional surface here. It's a 1 by 1 by 1 cube. And we're supposed to find the total flux out of this cube. So the divergence theorem says take the partial of F1 with respect to x plus F2 with respect to y plus F3 with respect to z, and then integrate this as a triple integral over this volume. All right, so for this problem, you're going to have x, y, and z are all going to go from 0 to 1. The partial derivatives, okay, this is going to be the partial derivative of negative y with respect to x. That's 0. And then the derivative of 1 with respect to y, that's 0. And the derivative of z with respect to z is 1. All right, and then times d, we'll call this dx, dy, and dz. Okay, so this one again is in the form that should be fairly easy to evaluate because we're going to evaluate a constant over this region. All right, so the volume of this region is 1, and then times 1. This answer is going to give us 1. Okay, so that makes that easy. We don't have to evaluate the integral over 6 sides. We can just use the divergence theorem, which is the beauty of that theorem. Okay, it allows us to integrate total outward flux without having to calculate the flux over every wall of that surface. Okay, we're just about there. This last question, the last two questions, is about finding outward flux over a cylindrical surface. And I think you can expect to see something like this on the test. All right, so this is, again, the vector field that explodes outward. This is a cylinder with a radius of 3, and this is going to be 4 units tall. So the cylinder looks something like this. Okay, it has a radius equal to 3 and has a height that is 4. And then the origin is going to be down here in the bottom of that surface. All right, so we're going to parameterize this surface in terms of cylindrical coordinates. So in cylindrical coordinates, this is going to be the radius times the cosine of theta, the radius times the sine of theta, and z is z. So this parameterization is going to be in terms of theta and z. And theta is going to go from 0 to 2 pi. We're going all the way around this thing, and this is going to go up to 4. Okay, so like we did before, we're going to say there's a point that's in this plane is going to produce a point that's on this cylinder. If we increase in the theta direction, we're going to increase around the cylinder this way. And then if we go this way, we're going to end up moving upward on the cylinder. This says find the outward flux, so we want to take the cross product in such a way that we end up with outward flux. So we're going to take r theta and then rz. All right, and then we're going to take the cross product of this. All right, so r theta is going to give me negative 3 sine theta and 3 cosine theta and 0. And then 0, 0, and 1. And then this is going to be times d theta and dz. All right, so we've got an integral that's going to go from 0 to 2 pi on theta. And it's going to go from 0 to 4 on z. The vector field is x, y, and z. So I'm going to replace that with this parameterization. 3 cosine of theta, 3 sine of theta, and z. That's going to get dotted with, I guess I didn't finish this. The cross product here is going to give me 3 cosine of theta. And then it's going to give me negative sine theta, and then change the sign. So 3 sine theta and 0. D theta and dz. All right, so this will be 3 cosine theta, 3 sine theta, and 0. D theta, dz. All right, so when you take the dot product of these, you're going to end up getting 9 cosine squared. And you're going to get plus 9 sine squared and 0. All right, so this is basically you're going to integrate. This thing is going to be 9. So 0 to 2 pi and 0 to 4. And again, because this is constant, and then it's d theta and dz, this is 9, and then this is a region that has an area of 8 pi. So if you take 8 pi times 9, that's going to give you 72 pi for the answer. Okay. If you're not comfortable doing that, just integrate 9 with respect to theta, plug in 0 and 2 pi, and then take the result of that, integrate it with respect to z, and plug in 0 and 4, and you're going to end up at 72 pi. Okay, then the last one is find the upward flux through the upper half of this sphere. This is a sphere with a radius of 4. And so the parameterization will be x is 4 sine phi times cosine of theta. Y is 4 sine phi sine of theta. And z is 4 cosine of phi. All right, and then when we set up this integral, you're going to have an integral that goes from 0 to 2 pi on theta. It's only the upper half of the sphere, so phi is going to go from 0 to pi over 2. All right, so this is on theta, this is on phi. All right, then the vector field is, again, x, y, z. So x is 4 sine phi cosine theta, 4 sine phi sine theta, 4 cosine of phi. That's going to get dotted with the one dA that I told you to memorize is sine phi cosine theta, sine phi sine theta, and cosine of phi times the radius squared. The radius squared is 16 times sine phi d phi d theta. All right, so 0 to 2 pi, 0 to pi over 2. We're going to take this and multiply by this. That's going to give me 4 sine squared phi cosine squared theta. This multiplied by this gives me plus 4 sine squared phi sine squared theta. Plus this multiplied by this, 4 cosine squared phi. All that's going to get multiplied by 16 sine phi d phi and d theta. Okay, now before you do any of the calculus here, it's important that you simplify this. And I'm going to take these first two terms and I'm going to consider pulling out a 4 and a sine squared phi. And if you take that out, you're going to be left with cosine squared theta and sine squared theta, which is 1. And then plus 4 cosine squared phi. So sine squared phi and cosine squared phi, that's going to give me 1. So all of this junk here is going to give me simply 4. Okay? Times the 16 is 64. I'm going to pull that constant all the way out. We're going to go from 0 to 2 pi, 0 to pi over 2. We've still got sine of phi in here. And then d phi and d theta. And I'm going to tell you that when you go through and evaluate this, you should end up with 128 pi for an answer. And I'm going to say that from there, once you get that cleaned up enough, it's fairly easy to evaluate. Okay, and we can't use the divergence theorem on this one because it is not a closed surface. And so we've got to really do this one with parameterizing the surface. Okay, I'm going to put this out tonight, and I will send everybody an email. And so when you get that, you can watch this video. I'm going to be in my office most of the morning tomorrow. So if you want to come in and see me, come in between like 8 and 11:30 or so. And then I've got class from 11:30 to 12:30, and then I won't be around much in the afternoon. So I hope this has been helpful, and if I don't see you tomorrow, I'll see you on Friday for the exam. Okay, see ya.